Hello, my name is Nestor. I'm a master's student from the Benemérita Universidad Autónoma de Puebla, and I'm going to talk about the measurement, the efficiency scale factors applied to a simplified dark model. As an introduction, despite the success of the standard model, some questions remain open, like neutrino mass, baryonic asymmetry, and dark matter. To try to solve it, the Large Hadron Collider answer was built to accelerate protons and collide at speed close to the light speed. One of the detectors of the LHC is the compact muon solenoid (CMS), and one of its main components is a superconductor solenoid with a 4 Tesla magnetic field, which is used to identify the detected particles. The subdetectors of the CMS are the tracking system, the electromagnetic and the hadronic calorimeter system, the superconductive solenoid, and the muon detectors. In this study, we care about jets, so let's talk about this. For jet reconstruction and identification, the hadronic calorimeter, made by scintillators and copper layers, is crucial because it can measure the energy and direction of the jets. However, due to the length of the hadronic calorimeter, it's necessary to use the rest of the subdetectors. These jets can be reconstructed using different algorithms. Examples are the Cambridge Ahen and NTKT sequential algorithms. In this study, we want to obtain the scale factors to correct the double B tagging Monte Carlo efficiency of a pair of big quarks. To calculate it, it's necessary to reconstruct the jets. For this reason, we use the NTKT algorithm with a distance parameter of 1.5 for fat jets. To identify these jets, we use the deep AK-15 algorithm, which returns probabilities for a jet from the decay from a pair of big quarks. This algorithm is based on machine learning techniques, using as input the list of particles flow candidates that comprise the jet and the list of secondary vertex. We can compose these probabilities into taggers to define our double bit tagging. But what does it mean bit tagging? It's an algorithm to identify jets from big quarks looking for displaced tracks and typically secondary jets within jets. This is possible due to the hadronization properties of the big quarks. To define our double bit tagging, we calculate the mass of the AK-15 jet and consider the resonance that decay into big quarks as Higgs and zeta boson decays. Once defined our reconstruction method, we obtain the scale factors to correct the double bit tagging Monte Carlo efficiency for a pair of big quarks. We use the output of the AK-15 tagger to define our tagger, with the efficiency defined as the number of events that satisfies the double bit tagging requirements divided by the total number of events. Finally, we obtain the scale factors by performing a fitting using the Higgs combine tool, which is used for statistical analysis in CMS. To perform our results, we use the mono-Higgs model frame, a simplified dark matter model, and which propose a Higgs boson in the dark sector decaying into standard model particles, predominantly into a pair of big quarks visible as a boost-like jet ray. The study considered fat jets with a PT greater than 160 GeV and eta less than 2.4. The plot shows contains all the uncertainties to achieve the best agreement between data and Monte Carlo, with the best scale factor possible as output. We define as pass category if the event with one jet is above a 90% probability of coming from a B pair resonance. Otherwise, we consider it as fail. In the table, we present the scale factors values for the considered engines, considering the years for the run to the LHC. As a conclusion, applying or double bit tagging, we obtain ad scale factors to correct the efficiency of the mono-Higgs model for 1-2 of the LHC. However, this method could be applied for other analyses which require efficiency calibration. And thanks for the time.